Welcome to this comprehensive lecture on electron flow and p-n junctions. In this session, we will deeply explore these fundamental concepts in electronics. By the end of this lecture, you will have a solid understanding of how electrons move in materials and why p-n junctions are essential in semiconductor devices. So let's get started. So let's start by understanding how electrons move within materials. Electrons are negatively charged particles that move in response to electric fields. So in conductors like metal, electrons move freely. In insulators, they mostly bound to the atoms. In semiconductors, electrons exhibit behavior somewhere in between. So this actually means that the electrons are negatively charged particles, and these particles move in response to electric field. So when these particles move freely in the material and it moves in one direction, and this is the current direction. As you can see in this image, we have two direction. We have the electron flow direction, and this is from the negative terminal to the positive terminal, but there is some other direction that called conventional current. We say that this is a non-physical term, but this is a conventional current, which means that we hypothetically say that the current runs from the positive to the negative. But the real thing on real life, on the physical, electrons are moving from the negative terminal to the positive terminal. So this is the electron flow direction, and this is the conventional current direction. So the electrons move freely through the conductor materials, and it moves according to the electric fields. And in insulators, the electrons are mostly bound to atoms, so it's going to be very hard for the electrons to move freely in the material. So if there is electric fields, it's not going to move freely, so there isn't going to be any current in this material. So that's why the insulators are the materials that we use to insulate ourselves or anything else from the current, because the electrons of this materials is very bound to the atoms, so it's not going to move when there is electric fields. Then we have the semiconductors. So the semiconductors, the electrons of the semiconductors exhibit behavior somewhere in between. So the behavior of the electrons is move, but not very freely. It's going to move a little bit in some conditions, like temperature. When we mix two materials together, there is so many conditions that the electrons is going to move inside the semiconductor materials. So that's why we use these materials in our electronic components. So what is the semiconductor structure? Semiconductors have a crystalline structure composed of atoms. These atoms form a lattice where electrons move between energy levels. The energy band structure of semiconductors is crucial for understanding electron flow. So this actually means, as you can see, that all of the all of the semiconductors materials have a crystalline structure, meaning that, as you can see, we have right here in this image six atoms. These six atoms are sharing their electrons. So as you can see, if we have right here, these two atoms are sharing these two electrons, and these two atoms are sharing these two electrons. And this is the silicon material. This is a type of semiconductor materials. So this is the silicon. We use the silicon in so many electronic components and so many electronic devices. So that is the semiconductor structure. We could, if we move or if we take one atom, this atom is going to be taken, it's going to replace it with holes. We are going to talk about holes in the next slides. So let's see the electron movement in the semiconductors. So So let's explore how electrons move within semiconductors. Electrons can jump from one energy level to another by absorbing or emitting energy. This movement creates charge carriers, which are essential for conduction. As you can see in this material, this is one of the many conditions that the semiconductors needs to make the electrons move freely. So in this condition, we have if this electron has an energy or received an energy, this electron is going to move from this place to the place that where the hole exists. So this is how the semiconductor or how the electrons move within the semiconductors. So the electrons can jump from one energy level to another by absorbing or emitting energy. So when this electron absorbs energy, it's going to move from one energy level to another. That's going to create a charge carriers, and this is the current. And also it could emit energy if this electron it is charged is going to emit energy, like for example the led emits energy and then return to its energy level, and this is how the electrons move within the semiconductors. So what is the formation of the p-n junction? So as we move forward, we will discuss the formation of p-n junctions. So, p-n junctions are crucial semiconductor structures created by joining B-type, aka excess of holes, B-type material, and this is why it's called p-n junction, because there is two types that are joined together. The first one is the p-type material, and this means that this material has excess of holes, and we have the n-type material, and the n-type material has excess of electrons. When we combine these materials together, it's going to form the p-n junction. This junction forms a boundary where interesting things happen. So this actually means that the p-n junction is created by joining b-type material and n-type material together, and there is going to be a boundary right here where interesting things are happening. We are going to explain this boundary or this place when we join these two materials together. There is going to be a place or boundary that is called depletion region. This region has so many things that happens inside it, and we are going to explain that in the next slides. So what is the depletion region? When p and n-type materials come together, they create a depletion region near the junction. This region lacks free charge carriers, creating an electric field that plays a pivotal role in the behavior of the junction. So this depletion region, when we have right here, as you can see, it's going to be created by joining the p-type material and the n-type material. So as you can see that the holes right here are empty holes, empty places for the electrons to move through it. And right here we have this material has stuffed with electrons. So when we put these two materials together, there's going to be a depletion region formation right here. Some of these electrons are going to be near the empty holes, and some of the holes is going to be near the n-type. By the way, this plus circles means that these are holes. So this is the depletion region. This depletion region is created when we join these two materials together. And this is the key role, or this is the place where the diode is going to play the role. We are going to explain the diode in the next lectures, but right here we are explaining the p-n junction. So what is the forward bias? So forward biasing a p-n junction means applying a voltage that allows electrons and holes to move across the junction freely. So we'll explore how this process affects electron flow and current. As you can see that the forward biasing right here is when we connect, for example, the positive terminal of the battery to the p materials and the negative terminal of the battery to the N materials. Okay, so this junction is going to be connected as forward bias. So this is what a forward bias actually is. So when we do this connection, the electrons is going to be pushed from the N-type material to the P-type material to the positive terminal of the battery. So it's going to be, the current is going to run, or it's going to flow through this circuit, because there is an energy right here that pushes the electrons. And also right here the depletion region is going to be very small, and this is, or also it's going to be very thin, and this is going to allow the electrons to flow through it, and also it's going to allow the current to flow in this circuit. So this is what a forward biasing actually is a type of connection to the PN junction. And by the way, the PN junction is a very simple, or it is the construction of the diode that we are going to explain in the next lecture. So what is the PN junction reverse bias? So we have explained the forward bias. Right now we are going to explain the reverse bias. So conversely, reverse biasing a p-n junction creates a barrier for electron flow. Understanding this behavior is crucial for diodes and other semiconductor devices that we are going to explain later. But right now we have the reverse bias connection. So the reverse bias connection is when we connect the positive terminal of the battery to the N-type material, and when we connect the negative terminal of the battery to the positive type material. This is wrong, by the way. Okay, so what's going to happen is that the depletion region is going to be so thick that it won't allow the current or the electrons to flow through the p-type materials. So that's why the reverse bias is going to is not going to allow the current to flow through the circuit. So that's what reverse bias actually is. So what are the applications of the PN junction? So to wrap up, let's discuss the practical applications of PN junctions. These junctions are the foundation of diodes, transistors, and solar cells, and other and so many electronic components. So making them indispensable in modern electronics. So the p-n junction, or the formation of this material by combining a p-type material and n-type material together, it is a revolutionary component that is used in so many things. So that in this in conclusion, we have delved into the intricate world of electron flow in semiconductors and the formation and the behavior of p-n junctions. These concepts are at the heart of electronic devices that shape our world. So thank you for joining this in-depth lecture. So thanks for watching, and I hope to see you in the next lecture.